Martens received his degree from the University of Heidelberg in 1994 from a hydron beam experiment at CERN. After that, he went to Japan to ICRR, Cosmic Ray Institute, to work on Super K and I guess the evolution of K to K. Too early. And in 2000, he moved to Utah, worked on the high res as well as the early TA experiment. And in 2008, he moved back to this new institute at that time, IPMU, later becoming Kavli-IPMU, working on his current experiment, XMASS, and also, Super K and TA that he had to be involved in. So I think this semester we had mostly domestic speakers, and also in terms of the subject, I thought this was appropriate. So we're going to hear from Professor Martens on results from and plans for the XMASS experiment at Kamioka Observatory. Okay,
Well, thank you very much for the nice introduction, George, and thank all of you for coming. Before I start, let me point out one thing that has not always helped me very much, but I would like to encourage you, and I'd like to encourage especially the students, to interrupt and ask questions. Do not be shy. Yeah? At some point we have to move on. I had planned for an hour. I was given 50 minutes, I just learned, so we will read through that. Yeah. So, partially because I was told this is also new to most of you, I will start off with a weak pointer, which I abandoned right away. Anybody saw that flicker? I saw it. It's out of battery. I will start out with a review of dark matter. This is essentially really just the fireworks of beautiful slides, Hubble Space Telescope and whatnot, simulations, to tell you the backdrop. And then I will move to our experiment, to our laboratory first, the Kamioka laboratory, and the XMASS experiment in its current incarnation, after I tell you what the grand master plan is here, and then tell you how we want to move on from here. Okay, so again, do not be shy, ask questions. We dive right into part one, dark matter. Now, this all started in 1933. Actually, there were two people, Karl Oort of Oort cloud fame and Fritz Zwicky, who used the term dark matter. Karl Oort measured the movement of stars in and out of the galactic plane, which, as you know, is going to be very difficult once you get to some distance from Earth, because you can only measure the velocity of stars in the line of sight. And if you look far enough away, that motion in and out of the plane is perpendicular to your line of sight, and that you cannot measure. So he wrote a paper also in 1933 or 1932 that said the same thing, like from this motion I would deduct that there's much more mass in the galactic plane if these guys stay in the plane than we see in stars. And here Zwicky was looking at a galaxy cluster, the Coma cluster, and here's a picture from his times. He had the best telescope and the best spectrograph, which is important to measure these velocities. Here is a modern Hubble Space Telescope type of picture of the same area, and here are some data. Yeah, so this is redshift translated into recessional velocity. How fast do they move away from us? And you see this spread. And the spread is what tells you what inside this cluster these velocities are. And you all have done the calculation of escape velocity from Earth. Yeah? So if you are too fast in a gravitational potential, you cannot stay in this potential. And this is the backbone of his argument. He looked at the galaxies, he pulled out all the formulas people had for what the galaxy mass is if that much light comes out, calculated how much mass is there, looked at the velocities, and figured out it doesn't add up. Viral theorem, yeah. So you use this to figure this out, and it can't stay together. It only can stay together if essentially 90% of the mass in this cluster, this is a modern figure, is dark. You don't see it. It's not in the galaxies. It's not in the stars. Well, it's in the galaxies to some large part. I'll show you a picture about this, because dark matter clumps where matter is clumped. Yeah. But it's not in the stars. It's not in the matter that we see. So that's how it started. And then Vera Rubin, actually already in 1975, she at this point now had the best spectrograph available and was able to measure slices of galaxies, so rotational curves of galaxies, and figure out that the velocity of stars going around the center of a galaxy essentially stays flat. Now, of course, as you go out, you include also more stars, but if you calculate it, you would expect still that the velocity would have to fall off for it to be on a circular orbit, stay on a circular orbit. This is what you see, this is what you expect. Who does this? Who pulls there to keep you on a circular orbit, to keep you in the galaxy? Again, the answer was like, well, we don't know, so dark matter, right?
So what are those things up down there?
Oh, this is just the other direction, I guess.
It's not because it says the redshift. No.
So this is redshift, so this is recessional velocity. And so I guess the whole thing goes with. Okay. Yeah, so, and only in 1980 did she finally write her paper about this. And finally now, in recent years, she gets the fame that she deserves for finding out about this. In the meantime, we have gotten much more sophisticated with all of this. We now use gravitational lensing to figure out how much mass there is that lenses. Yeah? So that would be strong lensing. It looks at if you have a galaxy somewhere and you see gravitational images from another galaxy in the far end, or a supernova in the far end, was this hypernova, Hubble, that then got resolved. Oh yeah, this was a supernova that was lensed by a very weak galaxy. You can figure out the matter distribution in between if you are lucky. Weak lensing, and I will tell you a little more about this, tells you about what happens to the light along its tortured path through all these matter distributions, all these gravitational pulls as it comes from far away. And so here are some spectacular photos that you can just download from the internet. I didn't have anything to do. I'm not an astronomer. I'm a particle physicist. So this is the backdrop to what we do, what we see. So if you do this, you use this strong lensing, this one picture here of a galaxy, to figure out what happens in between. Here is a very spectacular reconstruction of the mass in the middle. Yeah, you see here all these bent out of shape images of a far galaxy behind this galaxy cluster. Yeah? And so now you can use your supercomputers if you have them in your basement, but most people do this nowadays, yeah? You can figure out what kind of mass distribution it takes, and you have a picture also of the galaxy that sits in front of here, where that does the lensing. And then you come back with a mass distribution in this galaxy. And here now you see the individual stars, that's okay. But then you see the dark matter distribution outside of the galaxies. Yeah? And let me remind you that each individual galaxy again is largely dark matter. So everywhere we look in astronomy, we see dark matter. So weak lensing tells us a slightly different story. Again, these are all stolen. I didn't write the attribution here, where I stole it from. Stolen pictures, but so here you have your galaxies and you have your arms and like the whole universe now we know. I'll show you more about this in a second. Is a filament of matter and dark matter which are sitting in the same places essentially, with huge empty spaces in between. So here you have your filaments, you have some blobs of galaxy clusters or so on. And any photon that comes from the far end of the universe has to wiggle through there. And it feels gravity. Famously, Einstein's theory of general relativity was believed by people after the first total solar eclipse, when they figured out that the star that everybody knew is there had moved once you look at it past the sun, which you normally can't see because the sun just kills you with its light. Right? And so it's the same effect.
So that's the dark matter distribution?
Well, what was this? Something I am very sorry for. There was a small mark here that warned me about something. And I need to restart this. What is the, yes, largely, I mean, matter distribution is dark matter distribution, because dark matter is the one that that makes everything. Here we go.
So this nerve cell-like structure, that's the dark matter?
Yes, I guess in this illustration, this is like the dark matter, the filaments. No.
But the colored blobs are galaxies.
Well, galaxy clusters on this scale, I would think, yeah, because if this is the dark matter distribution, then you have the filaments. I mean, like, let's come back to your question in a second when I show you the SSDS matter distribution, yeah, where we see these filaments. Right?
Yeah,
this is an artist rendition.
Just want to understand the figure.
Yeah. Well, it's an artist rendition to explain how light has to wiggle through there. Right? And so here is what really happens. Normally the galaxies are on all kinds of orientations, no? And then you saw before how the strong lensing bends these galaxies into arcs around the, so this banana shape or so. So you see these things. Here you don't see banana shapes. This is, you really need strong lensing. But you see all of a sudden, along these passes, these different passes, that things get aligned, which were rather randomly distributed. You see, this looks a little tilted towards here. The axis that you draw through it is different. So the axes get aligned in the same neighborhood on your picture when you look out. Yeah, that is how you identify weak lensing as opposed to strong lensing. So it's a much more complicated analysis which looks at correlations between neighboring imaged objects. Yeah? But you can use that now to look back, and then you also run your simulation again. Yeah? You run a simulation and you look how the universe is supposed to have evolved. And it all, started with a big bang, inflation, big bang, inflation, and then it evolved. First stars, cosmic microwave background, afterglow. And with time, the gravity of dark matter pulls everything in. Yeah? Matter is only 5% of the total matter content of the universe. Dark matter is really what dominates gravity. And so everything aligns, and here you see already these filaments. And then now we have these people who did the Sloan Digital Sky Survey. In the meantime, it's like in its umpteenth update instantiation. It's Sloan Digital. I think we are beyond 3, right? This was stopped in 2014. This is a telescope, and here's how they looked out. The problem is your average telescope, your garden variety telescope that you may even have in your closet at home, is it looks at a very, very small patch in the sky. This thing looks at a huge patch in the sky, for a telescope that is, yeah? It's not like your fisheye lens, which takes the whole sky in one shot. And it does spectroscopy. So it tells you the redshifts. It tells you how far out these things are. And that is how you get this beautiful map. And I guess you all know why there are these cones where we don't see anything. That's a galactic plane. Yeah, you get stuck in the galaxy. You look at the stars of your own of our own galaxy, of the Milky Way, and you can't see anything. But above and below the Milky Way, you can figure out how far away the galaxies are. The galaxies outside of our Milky Way. And you see these filaments, yeah, Great Wall, and they have names now, like that. You see the structure of filaments and empty spaces. And I guess the gray shades were just symbolizing that, yeah, for educational purposes.
So they only go up to redshift of 0.015?
Well, so here you go. You have to, you're between a rock and a hard place. Yeah? If you have a large aperture, if you take in a wide angular view, you collect relatively little light from an individual thing. There's a Hubble Space Telescope, can go deep field, can go out very, very far. Very narrow field of view. Right? So if you want to cover all this area in the sky, you can't go out that far. Yeah?
So Kai,
Yes.
I'm
Yeah.
nothing about it. So
Good.
very stick. When for the non-expert like me, what do I see?
What do you see here?
Yeah.
You see essentially matter distribution. So this redshift is distance. It's a measure of distance out into the universe. Yeah? And so what they do is they point the telescope and look at one beam out here. And in this picture, they see many, many different galaxies. With the spectrometer that they have, measuring 5 colors, they can figure out how far out that thing is. And so this gives you a dot. Now red here means many, many galaxies at that distance, yeah? And blue means like 1 or 2, yeah? It's a scatter plot, essentially. Yeah? So, and this whole thing collapsed into a plane, which is essentially a core. Yeah? Yeah? But so this tells you at this distance, yeah, here is a distance at which there are no galaxies for quite a redshift range. So this is a void in the universe. No? And then you have these filaments that evolved, and we have time to go back. This is what our simulations of how matter clusters under the influence of matter and dark matter. And this is what we expect, and this is what we see. Yeah. And so now you can run your simulations through various compositions of matter and dark matter, and you choose the one that gives you this kind of granularity, this ratio of like how thick or thin these fibers are compared to the voids in between. Yeah? That's one way to constrain the history of the universe, and especially the mix of matter and dark matter.
Well, it must be a wedge. It cannot be as wide, in this vertical direction. Otherwise, I guess you will not find voids.
You're probably right. Yes.
Probably
So
from
the
theta angle. And then it can help
right. If you, because that's the same as what you're saying is right, because if you project this angularly out here, then you smooth out this. You're right. And what I said is we smoothed it out in this direction, and this is probably not tenable. But on the other, yeah, and also you see that there is not, you would have a much higher density here unless you normalize that back out. If you, okay. But I guess everybody gets the idea of this.
Okay. So in other words, in those blue one things is you simulate measure.
This is measured.
This measure, but the one that is
the blue are simulations.
Simulate. So this means they indicate that you understand what is dark matter.
You understand how much dark matter you need to get this.
Yes. So you know the dark matter properties and physics and so on and so on.
No. Dark matter is just gravitational with mass. That's it.
Right.
But you're right in the sense that the difference to dark energy is we think it's particulate because it behaves exactly like matter does, yeah, and it is not a property, a uniform property of space, yeah, that just pulls, because then it would not do this, it would not cluster. Right? So it's particles, it behaves like particles in gravitational. Right?
Yeah. You also assume the initial condition, the
That's
initial
correct.
perturbation, 10 to the minus 5 or something.
That's correct.
You can
And we
adjust
will
that
get
as
to
a
the
free
initial.
parameter to see how things.
But technically, how do you compare this your simulation result with the measurements?
You calculate correlation coefficients essentially, right? Angular correlations in your. Right?
It's probably minimization.
Yeah. So, and let me repeat, this is background information. This is not my own research. Yeah, Ethan?
No, as you have said, this stone digital observations are luminous part. So
Right.
these are just ordinary.
This is the matter, but the matter traces dark matter because the gravitational potential
Right.
is done by 95% of the matter, which is the dark matter. Okay, so now here is a lot of measurements, and we don't have time to really go into this, where these correlations, these density fluctuations are parameterized as a function of scale, of distance, yeah? Like, and so these are the different measurements that you get from, for example, supernova, SDSS, Sloan Digital Sky Surveys in their cluster abundance. Actually, the cosmic microwave background, which we'll come to in a second, is in there. And you see, this is what we call the cold dark matter paradigm, which is what I told you about, which is that this is heavy particles, yeah, that clump together. It can't be hot dark matter, so it means it can't be neutrinos. Yeah? So you have dark matter, you have stuff that you don't see. What do we know is stuff that we don't see? Well, neutrinos are stuff that we don't see. So in our inventory of known physics entities, neutrinos are the natural candidate to do this. But we know these guys are very light, so they have to be relativistic. So they will not be bound in gravitational potentials because they are light, they are fast enough to just zip out. And this would mean that you would not have structure as we see it here. But if you look carefully, there's a discrepancy here at small angular scales, yeah? And this is something we have to contend with. But overall, this is a huge success story. Okay, and so here's one other aspect of this now with the Hubble. They looked as far back. With the Hubble, you can really look far out. Yeah? With SSDS, you cannot. But with the Hubble, you can. And so then you take all this time to take all these exposures, which takes a long, long time with the Hubble, because the field of view is so small. That's why it can look so far. And patch this together, and then in this cone, from weak lensing, from these correlations between the shapes of galaxies at the various redshifts, you reconstruct how clumpy the matter is. And you can see what I told you as a story in this, what I showed you in the simulation, yeah? How a relatively homogeneous universe coming out of the Big Bang increasingly clumps together in these gravitational potentials of the dark matter structure and backbone, yeah, which is a self-reinforcing process. Yeah? And so nearby, in early days, you have this fractured picture, and it gets smoother and smoother as you go out. All very fascinating measurements. Here we have, of course, the most famous cosmic microwave background, and I remind you, this is how it's taken. You really have to subtract the foregrounds out to get these very smooth pictures. But once you analyze them, and please, I do not know the analysis technology behind here. But you get these we will see temperature fluctuations or angular correlations, if you wish, in this picture as a function of angular scale or multipole moment, whatever multipole of spherical harmonics. Yeah, what is the weight in a certain spherical harmonic in this picture? That's what we see here. Yeah. And you see the progress. These are, you can just count the bumps, yeah? 1, 2, that's where W map bailed out, and now Planck went here, and the next one, the next satellite is in the making. And so here is, you can look at this, the PDF is available later, I hope. Yeah, you can look at this in your free time, because this is again stolen, and I hope I did not